I'm Brian DeLuca, and I am here with Art Gonski in Nexperia's booth at APEC 2025. Art is going to show us something in the GaN area.
Art Gonski, I'm the Power Applications Engineer for WIM, and we're going to talk about APEC 8-in-1 evaluation board, the best it gets. And what it's used for is dynamic characterization and application testing for just about any application out there, and it's our Nexperia first topside-cooled silicon carbide MOSFET. Next to perfect. The demonstrator is, the eval board comes with 4 APEC top cooling FETs with a heatsink that is available to go right on top on FET. So the key features: adjustable switching speed and gate voltage through adapter boards for the gate resistance in particular, and that's the adapter board itself. And you can change the resistors and even some caps online directly. Includes a current measurement by coaxial shunt, so you can do direct measurement here, and noise reduced virtually to zero. Enhanced PCB design to minimize inductance, and work with the single half bridge paralleling or 2 half bridges if you want to parallel devices, or want to use the H bridge, which gives you availability and sort of a freedom to do that. Easily adaptable for continuous operation. Also, you can do the peak measurements and double pulsing with the heatsink that's provided with it. The next step is, if you can think of a high power, high voltage type application, you can use it, and you can use it pretty much in charging stations, uninterruptible power supplies, solar power, photovoltaic type applications, electric vehicles, of course, battery energy storage systems, and the motor drivers themselves.
Okay, so it's used for bigger applications.
Yes, so something in the higher voltage, higher power application, silicon carbide is perfect for it, because it has the thermal capabilities of the best of any FET, or I call it power switch for that matter, right? The topologies, you can use just about anything with a single power factor correction switch, or you can use it as a 6-pack for the motor driver, which is the best application for this particular, for the silicon carbide devices, for an LLC full bridge DC to DC conversion, which is prevalent in data centers, for example, from 400 volts down to 48, and from 48 down to 12 or 5 or 3.3. And basically, this is our basic cell. This is the half bridge. There's 2 of them on this board. This is actual life. This is actual life. The switching losses, of course, it'll go up, but we are the best of, in this case, of just about everybody, because our gate capacitance is lower than anybody else's, and the gate is 2.2 milliohms, so it's easier to drive. That's measured at the 25 degrees C room temperature, but it gets better at the higher voltages. At the higher temperatures. The 800 volts, basically 30 amps out, 18 volts minus 5 on the gate, 18 to turn it on, minus 5 to turn it off. And as you see, this is fairly flat as we start establishing that. So the flatter it is, the better. And we get the flattest at this point. The RDSO and stability for high load conditions, which is an extremely important function. The RDSO and stability, all the way up to 175 degrees, stay within 25%, where everybody else just rockets up to 85% of their original value, which also conducive to a lot of switching losses, a lot of power dissipation, wasted energy, right? And so that's the issue. We have much lower package inductance compared to through-hole equivalent, and we have designed original, long time ago, LF pack application with a clip or the bus bar internal, and assembly atomization advantage of the SMD, especially in this package. The thermal performance is equal as through-hole equivalent, except you use a smaller heatsink, and you can just bolt it right on top of it. Topside cooling keeps the heat off the PCB for much cooler and more reliable performance, and you don't blame the layout guys any longer. Everything to the mechanical guys, so that's important, right?
So that's a good question. What do engineers need to think about when they're designing this into their systems?
The interesting thing is not just engineers. I'm finding out, because I've been at Silicon Carbide for the last 10, 12 years, I'm finding out that people are finally starting to ask questions why. Why should we use silicon carbide? Why should we use GaN? And I've made slides about 10 years ago, why? So essentially, once we start pumping up the frequency, the efficiency will be increased and the components, passive, will be reduced. I don't want to put the inductor guys and the capacitor guys out of business, but let's make it smaller. Let's go planar. And I think this is where the technology is going. And so the sustainability is important. The copper is getting expensive by the year because it's not infinite supply. The capacitors are not cheap. So this part actually will be third cost on the bill of material.
Gotcha.
Capacitor inductor is going to be number one
Yeah.
and number two, right? And so this is what we're trying to achieve. Also, wasted energy and sustainability, which is becoming an issue right now worldwide.
Yeah.
And so that's how we operate with that. And here's the product. So this is our famous TO2247-3. It's an old design, old package. Not as old as me, but close. but close. And we're down to about 17 milliohms, which is a great RDS zone with such a low capacitance. The 4-pin, which gives you better thermals for something like that.
Yeah.
We're coming out shortly with that. TO263-7, that's a D-square pack. And so topside cooling parts are right now coming out. And this is pretty much right here, the X pack and the QD pack, which is also top cooling. Will have better thermals than the X pack.
Okay.
So
Well,
we're working on that.
Awesome. Thank you so much
Yeah.
for sharing with me.